All right, gang, so it is time for the second part of Chapter 6 where we need to go through the two types of ossification processes, and then we need to start looking at the nutrients of how blood is getting to the bone cells. We need to look at more about the matrix, more about control of calcium in the matrix, and then a little bit on bone growth, bone adaptions, and fractures. So this hopefully will be a quick review of some of this material, because hopefully you have already read it and are slowly letting it marinate in your brain to prepare for our upcoming test 2. Okay, let's see, here we are. So we talked about in our last lecture that osseous tissue, which is bone, a type of specialized connective tissue, has the 4 ways we can define the cells as trapped mature cells as osteocytes. In the periosteum, we're going to have your osteoblasts, osteoclasts, and your osteoprogenitor cells. And you also have that on the endosteum. We talked about long bones and flat bones and how the compact bone is the osteon, and osteons are the functional unit, and you have interstitial lamellae kind of plugging the holes between the osteons. And then you have circumferential lamellae. And then we have a growth that can occur in the periosteum with the cells adding to the circumferential lamellae for your, what do you call it, your appositional long bone growth. For your endosteum or your trabecular spongy bone, we can add more kind of layering, again, with that protective periosteum wrapping and increase those pillars that form the trabecular spongy bone and grow them as well. But how did we get bone in the first place? So if we go back to cells that are part of a blastocyst, the cells are going to form into these germinative layers. And eventually some of those cells are going to form into some dermal type tissue that can become bone, and others will form into cartilage. So hyaline cartilage, which is going to give rise to many of our long bones, is going to be part of our skeletal system, and part of getting the bones to transition is one part of skeletal ossification processes. Now, our skeletal system does retain some cartilage for the duration of our lifetime. So think about costal cartilage, the cartilage in our nose, the cartilage in our ears, the epiglottal cartilage. So some of this hyaline cartilage does stay cartilage for the duration of our life, but we are, in the purposes of learning about some of our ossification processes, we are interested in learning how does hyaline cartilage transition into becoming bone tissue. Now, for a review of hyaline cartilage, when we look at cartilage tissue, we call the cells residing in cartilage chondrocytes. Chondrocytes are going to live in a little bit of a protective barrier chamber, and that barrier chamber protection is known as the lacunae. For our cartilage matrix, it is non-vascular, so there's no blood vessels in there. But it is going to have a little bit of water, a little bit of ions, but it's more of a protoglycan protein. There can be collagen, there can be some elastin fibers, and the cells are suspended in this matrix, and it's not quite solid and it's not quite fluid. So it's a little bit of a jellyish matrix in the middle between fluid and solid. All right. The matrix and the chondrocytes and the cartilage actually are physically separated by a perichondrium. So like the bone, there's a protectiveness of connective tissue that physically separates the cartilage cells and the matrix of the cartilage from external other tissues. So if you look at the pictures below, this again here is showing our chondrocytes, and our chondrocytes are wrapped in a protective chamber, and the protective chamber is the lacunae. And if this is going to be cartilage that converts eventually to bone, what will happen is the cells, the chondrocytes in these lacunae will transition into becoming osteocytes, and the matrix here will become more of a calcium-rich, solid matrix that blood vessels can push and channel into, and our cells will become osteocytes, okay? Now, looking at, just like with bone, we see that there's a physical separation of cartilage material from other tissue, and it's done by this perichondrium connective tissue layering. And the perichondrium, much like a periosteum, is going to have some cells that kind of live near this chondrocyte-rich matrix environment. It is a connective tissue material, so it could be fibroblasts, it can be immune cells, and they are going to lay down some collagen and elastin fibers. And those collagen and elastin fibers are going to make that protective covering that becomes the outer part of the perichondrium. Okay. Now, when we want to grow cartilage, much like bone, sometimes we want to grow cartilage in a length type direction, so we want our long bones to get longer, and other times we want to get our growth to be in width. So we want our nose to get fatter with our face, our ears to grow not only upwards but outwards. So the type of growth that is normally associated with growth at the margin of cartilage and perichondrium, it's the same words we use when the bones grow in width at the margin of where the bone matrix and the periosteum is going to be our appositional growth. And so in this type of growth, for appositional growth, we're talking about trying to make the actual bone or the cartilage tissue push the perichondrium out a little bit more. All right, and so appositional growth is it's the cells within the perichondrium, the margin area of the matrix of the cartilage that live closest to the perichondrium are going to undergo growth and are going to lay down matrix, and now as they do so, they are going to push the perichondrium, the protective covering, to grow outwards. And by growing outwards, we're making the actual amount of tissue thicker. So for appositional growth, again, you're looking at that margin of where the perichondrium and the cartilage intersect, and what's happening is cells within this area are becoming chondrocytes, are beginning to lay down matrix, and are growing a larger area for the cartilage material, and in the case of bone material, to expand out. Okay? Now, in the bone, you'll also see ossification. You'll see the vascular network grow, but for cartilage, again, it stays avascular, so appositional growth is somewhat how we get the bones to grow thicker, to grow out, the cartilage grow thicker, but it does not give rise to, for cartilage purposes, vascularness to the matrix, okay? Now, interstitial growth is what we see more here. This is how do we get the bones to grow longer. Now, in our long bones, as we ossify, you know, the bone tissue is becoming solid matrix trap cells. So we depend upon the cartilage that remains in our metaepiphysis regions to continue to divide cells, and as the cells divide and they separate from each other, they then lay down more matrix between them. And in doing so, a long bone becomes longer because in that area that the cartilage is living, they are pushing out, pushing upwards and downwards, and allowing the bone to become bigger, become longer. Okay, and this is what's happening in our growth plates. And so that's part of the reason why when fractures occur in the growth plate, they're really worried about it, because we need this population of cartilage to continue to maintain itself and maintain an ability to push cells towards the center, towards the ends, and then those cells on the margins, as they ossify, allow us to continue to maintain a cartilage as the bone is growing both in length and height. All right, so with bone formation and growth, All right, our bones technically are going to grow until we, around the age 25, when most of our long bones are going to fully ossify. And the cartilage that's present in those growth plates, in those metaepiphyseal areas, are no longer cartilage cells and fully complete a changeover to become bone ossified cells and matrix. All right? Now, the flat bones and other areas of our body give rise to bone tissue in a different way. They're not converting from cartilage. And so that, again, process will happen because the dermal tissue, the connective tissue origination into bone, is going to undergo an intramembranous ossification. And both of these processes seem to end around 25 years of age. And so at that point, your bones are no longer going to be able to increase in length and height, and so you should be done growing with your height. All right? So part of getting bones to grow is transitioning the dermal or the cartilage tissue that is there into bone tissue. And so that is converting the matrix from a dermal background, collagen-rich material to a matrix of bone, which is collagen and calcium mixing, or in the case of cartilage, taking a cartilage matrix, which is avascular and protoglycan and jelly-like substance, to a solid calcium phosphate, calcium carbonate, collagen mixture, solid matrix. All right? So ossification of the matrix involves depositing calcium into the matrix, and this process of depositing calcium is called calcification. Okay? Now, our cells are going to continue to grow and divide, and in doing so, can lay down, again, more matrix around them, and so that is part of what osteogenesis. So if the cells are dividing and adding to the matrix, we call it osteogenesis. All right, so the first type of long bone growth, the type of bone development that comes from cartilage cells, is known as endochondral ossification. So in the name, we know that we are going to convert cartilage into bone. Right? And this is how your humerus, your femurs, many of the long bones derive, because they originate in your little fetus embryo self as cartilage and eventually have to undergo a change to become areas of bone and vascular rich networks. All right, so in our book, there's a spotlight, figure 610 on endochondral ossification. That's what this slide is trying to talk us through. So some of the keys for endochondral ossification is: 1, hyaline cartilage is our originating tissue. 2, hyaline cartilage is going to undergo a vascular network pushing in. And as that vascular network pushes in, cartilage matrix, which wants to stay avascular, can no longer stay avascular. It starts to develop blood pushing through. And so that is one of the key steps that leads to these what's known as areas of ossification. The matrix transitioning from cartilage matrix to bone matrix, and the transition of chondrocytes into trapped bone cells, so osteocytes. Okay? Now, the cartilage that remains is going to slowly get trapped in these areas between the epiphysis and the diaphysis. And they are going to be called your endochondral plate, your epiphyseal plates, your growth plates. And as long as cartilage is there, the cartilage can undergo interstitial growth as well as appositional growth, and it can continue to maintain itself as the bone grows in length for interstitial growth of the bone and with appositional growth of the bone. Okay? So, step 1 is cartilage, which wants to stay avascular, which cells make the chondrocytes make type of anti-vascular growing molecules, so the blood vessels do not want to grow into the tissue, suddenly have a stoppage of this anti-vascular making molecule. And as the cells begin to stop making the vessel anti-vascularness occurring, what we're going to see is that blood vessels are going to start to grow closer to the cartilage, and they are going to start to transition some areas of that bone or that future bone into a passageway for the vessel to grow into. And so the first 3 steps here, all right, are all about the transition of the system for cartilage to be less anti-blood vessel, and blood vessels start to grow in and near the outer region and then push into the center of the bone. Now, once the blood vessel pushes into the center of this, what will become bone, we now have what's known as this primary ossification site. And so fibroblasts are going to migrate with the blood vessel and are going to help produce what will be a little area of spongy bone, trabecular bone, and an endosteum. All right, and so that area is going to start to hollow out somewhat and is going to be an area that we are going to transition from cartilage and jelly and non-space matrix to calcium phosphate, calcium carbonate, collagen-rich space around these transitioning chondrocytes to osteocytes, and an open network of spongy bone developing. Okay, and that primary ossification center is going to spread and eventually lead to, as we see here, a more open chamber that is pushing the cartilage and the epiphysis above it and pushing the cartilage and the epiphysis below it to become further separated from one another. Okay? Now, because of the perichondrium, because of the endochondrium, we still have cells that are stem cells that can become more bone cells and lay down more matrix. And so what we're going to see is in and around this medullary cavity, we're going to start to add osteocytes, we're going to start to add more matrix, and we're going to start to see a thickening of that area between the perichondrium or periosteum and the endosteum. Okay? Okay. Now, we've gotten to this part where this original cartilage bone-ish type feature, this kind of future long bone, has become now a cartilage-rich epiphysis, proximal and distal epiphysis, and a ossification, osseous transitioning tissue in its center. Now, to get the epiphysis to now start to transition and ossify, we are going to see another blood vessel transition into the epiphysis central area. And so what we're going to see is now a secondary ossification site in each epiphysis. And that secondary ossification site, just like the primary, is going to lead to a transition of a little bit of spongy bone developing in the center. We're going to see again some more fibroblasts come in here in assistance with making this open network area. And then we're going to see transition in that perichondrium, periosteum area, more osteoblasts and osteoprogenitor cells start to lay down ossified calcium-rich matrix and collagen-rich matrix, and the cartilage is going to slowly be pushed to the margins. All right? We now see what will become this kind of cartilage-rich region that is going to give rise to eventually our epithelial cartilage, our growth plate, our point of continual long bone interstitial growth as the individual continues to grow until about 25 years of age. Now, at one point, we're going to see the around 20, 25 years. Usually we see this with the a little bit of assistance and push from testosterone and puberty, that these cartilage-rich epithelial plates, growth plates, are going to finish ossifying and are going to become what will then be seen in our X-rays, a ossified-rich area that'll be known as your apophyseal line. And at that point, when the cartilage completely transitions to bone matrix and we lose those chondrocytes and we lose the ability then to continue to push the bone to grow in a interstitial type format, we are going to see that the long bones are fully formed and no longer going to be able to grow in height. Okay. Now, some of this cartilage out on the margin of the epiphysis is going to eventually turn into what will become articular cartilage. And articular cartilage is going to remain with us for our lifetime, and in many of these bones is going to be the cartilage that helps in the formation of synovial joints. So the bone matrix never actually touches the other bone's matrix, and so it becomes that kind of cushioning and that kind of tissue that allows for some movement and without breaking or fracturing or tearing into the matrix of the bone. Okay? All right. Compare this again. Endochondral ossification, we have interstitial growth occurring. So these growth chondrocytes start going through a division and start pushing and making matrix between them. And that is how they grow and add to the length of the bone. As the margin of where these cells line up and start to get near the ossification centers, we see the bone cells undergo a transition into what will become trapped cells that give rise to bone cells, and the matrix transitions from jelly avasculature to more of a ossified, calcium-rich bone collagen matrix. Okay. All right, and if we look at the actual cartilage, we see we can divide it into different areas. We can divide the cell areas that are cartilage and lacunae that are still undergoing mitosis and pushing each other away as their lacunae separate and putting matrix between them as a proliferation zone. As the cells start to get nearer to the ossification centers, they're going to grow into larger cells. They're going to try to hypertrophy. And then as we see the matrix transition from being what is true cartilage matrix with a little bit of proteoglycans, jelly, and some collagen and elastin into a calcium-rich area, we're going to see a calcification zone. The matrix is not fully bone matrix, so that is why it's a calcification zone, and the cells haven't fully become dead chondrocytes and are transitioned into becoming osteocytes, so then that is still somewhat a cartilage area, the calcification zone. But when we look at the final component where we see bone tissue proper, we see that it's osteoclasts, osteoblasts, osteoprogenitor cells, and osteocytes, and we see that calcium-rich matrix is now beginning to become a solid matrix with collagen and a true bone matrix. Okay. So when we look at these cartilage areas in many of our developing long bones, so you look at the phalangeal bones of your fingers and toes, you look at your long bones, your humerus, your radial, your ulna, your femurs, your tibias, your fibulas of your legs, we can see in young people under the age of 25, even more clearly if you haven't gone through puberty, that if we take if we take x-rays, we can see that the cartilage-rich areas do not show up so well on a x-ray. And so we can see the matrix, cartilage-rich matrix showing up as dark spots, and so we see those epiphyseal cartilage lines. We see those growth plates. We see those cartilage-rich areas. If we take a x-ray of an adult that has undergone full ossification and bone growth, and the epiphyseal lines have ossified and the areas of articular cartilage have thinned out to be just a little bit of cartilage-rich where two bones intersect, we see that the dark spots are less pronounced, less formed, and we see more of these bonish articular cartilage regions, all right? And the epiphyseal lines are basically disappearing because we don't see the cartilage-rich inside the bone, long bone areas. Okay, so one of the ways you can see if a child has gone through puberty is to look at their x-rays and see how much epiphyseal as well as articular cartilage remains in their growing long bone areas versus a child or a person that has finished and been through puberty and finished growing. Their bones are going to have less pronounced matrix of cartilage-rich regions in the long bone growth and epiphyseal lines. Okay. Now, we can continue to push the bones to grow in diameter. So when you look at a kid, you know, a kid's circumference around their knees, around their ankles is really, really small. And when you look at an adult, you know, we've thickened up. We've gotten larger as we've grown taller and added more weight bearing to the stimuli on the bones. So we need the bones to grow in a width type direction. And again, this appositional growth of bones is occurring at the periosteum and the bone matrix intersection. And so we know we have some different cell populations in that periosteum cell layer to include osteoblasts, osteoclasts, osteoprogenitor cells, and they can continue to lay down and add circumferential lamellae. They can continue to add circumferential, more of an osteon growing growth, and so we can add to the appositional areas more osteons, more interstitial lamellae, and then we can add more circumferential laminae. And so the picture here is just showing you how that occurs. So we end up with perforating areas for blood vessels to continue to push into the medullary cavity, and then we can end up growing central canals if we grow some osteons within the growth plates or growth areas of the periosteum bone matrix. Okay. Now, not every bone wants to grow longer and taller. So a large portion of our bones are not long bones. We have some short bones, we have flat bones, we have irregular bones. These non-long bones do not undergo endochondral ossification. So they have to be derived in a different process. And that process in many cases needs to have a origin not from cartilage but from other types of connective tissue. And so that is why we call it intramembranous or dermal ossification, because we're going to give rise to ossified bone from connective tissue, dermal type connective tissue, rather than your cartilage. Right? Your skull bones come from this. So when you're born, remember the bones are not fully ossified into each other. Their sutural joints haven't completely been made. And so your head kind of forms a cone head as it's pushed out of the birth canal. And the fontanelles is what we call those soft spots of dermal tissue that are going to eventually transition into bone and form the ossified sutural joints that will give rise to our skull. Okay. The lower jaw, the mandible, is going to derive from dermal bones. Your collarbone, your clavicle is going to derive from this type of ossification process. And so what we see in this ossification process is we have a dermal-rich mesenchymal cell with collagen, elastin around it that is going to transition into becoming less of a dermal tissue and more of a ossified bone area. And so we are going to see that mesenchymal cells are going to aggregate together. They are going to differentiate into osteoblasts, and then just like an ossification in our endochondral bones, we're going to see a transition from the dermal tissue and collagen-rich non-calcium deposited matrix turn into a calcium carbonate, calcium phosphate collagen matrix. And then as that happens, we are going to grow that ossified bone matrix around the blood vessels that may already exist and form our spongy trabecular bone with a periosteum that'll then allow us to encase this bone in a separate region, separate from connective tissue outside of the bone. Okay? So the summary is two big major types of bone growth, bone formation. We take cartilage and convert it to bone for many of our long bones. For many of our flat, irregular, other bones, we take dermal tissue and convert it into bone. Neither is better than the other. They are just two separate ways in which bones form. They both can give rise to areas of spongy trabecular bone and areas of compact bone. And then both will give rise to a periosteum that is going to separate the bone matrix from the outlying other tissues around it. Okay? Now, bone is vascular. So in our long bones, we saw one of the big ways to lead to the primary ossification was to have a blood vessel come into that center region and then push into the medulla. that is our primary nutrient artery and vein that eventually pushed into the diaphysis region of the long bone and gave rise to a blood network that runs north and south in the medullary cavity. Remember that we had a separate area developed for secondary ossification in the epiphysis. And so what we see is that area eventually got kind of part of the metaepiphysis, the middle region where the diaphysis and epiphysis meet. And so the remnants of that second vessel that pushes into what was in the secondary ossification centers are your metaepiphyseal artery and veins. All right? Now, not every vessel is trying to grow into the bone. We are going to see a large number of vessels try to grow into our periosteal regions, and so those will be our periosteal vessels. They are going to continue to help provide blood supply to the cells in the cellular region of the periosteum that can eventually lay down more bone matrix, continuing to ossify and epositional growth for the bone, as well as the connective tissue components. Okay, so if you had to look at bone and the blood supply into the bone, most of the blood supply in the medulla region, the center region where the yellow bone marrow is living, is going to come from that primary nutrient artery and vein. When we look at the epiphyseal areas, which is spongy bone rich and full of red bone marrow, the blood going in and out to that region of the proximal and distal epiphyseal part of the bones is going to be getting most of the blood from a metaepiphyseal vessel. And then we see that the perichondrium vessels still come in and provide blood supply to the cells that live in our cellular layer of our periosteal type regions. Okay? Now, bones are going to still need to be stimulated and modified for nervous growth, so to get an idea of weight and tensile lines. So a little bit of the nerves that we see coming into and around bones are only going to come into the periosteum, and they are going to again provide sensory information and feedback, so we ensure that bone growth occurs in uniform type patterns along the whole endosteal, whole medullary canals, epiphyseal regions, so we don't end up with abnormal growth areas. Okay? The sensory nerves do carry information of injury and pain for bones back to the central nervous system. Okay? For how do we trigger bones after we've grown them to a certain point, so they know to grow thicker, grow longer, grow wider? So bones develop in some of our long bone manners along a certain way that the weight will be carried across the epiphysis and the diaphysis regions. And so what we see is that bone is designed to maximize its ability to carry weight on these tension lines. And so the tension lines come from the orientation of the bone in the joint, the orientation of when the body is in a standing anatomical position, that the bones are best carrying the force distributed amongst its optimal compact and spongy bone regions. All right, and so if something is to happen to the way the body is carried, so if something happens and the body is going to be carrying itself heavier on the right side than the left side, what we'll see is that the bone will then grow in the response to the way the body carries itself. So look at tennis players. Tennis players have a dominant hand, that's their forehand. If we look at the bone thickness of the radial, ulna, and humerus in their dominant hand, that does a forehand and a backhand and plays a role in absorbing the tension that comes from the ball striking the racket almost every time the ball does strike the racket. That dominant bone on the dominant hand is thicker than the non-dominant hand. So if you look at Roger Federer's forehand versus his backhand, his dominant hand versus his non-dominant hand, we'll actually probably notice that the radius and the ulna is thicker on that dominant hand than it is on a non-dominant hand. And it goes back to that dominant hand is used to carrying a heavier load and having to respond to more tension and adapt to more weight being and force being applied than the non-dominant hand. And so we see that the adaptation is more appositional growth has occurred on the bones in that dominant hand versus the non-dominant hand. All right? If you look at the tibia bone versus the fibular bone in your lower limbs of your legs, the tibial bone, tibia, is the weight-bearing bone. So what we see is appositional growth on the tibia bone is much thicker. That bone develops thicker and bigger than our fibulas. In fact, your fibula is a non-weight-bearing bone, and that's part of the reason, I guess, one of the Super Bowl guys was playing this last Super Bowl with a broken fibula. It is not a weight-bearing bone. So while it might have been discomforting or painful to be, you know, touched or engaged in some type of physical contact, for the most part, that fibula bone is not weight-bearing, so it doesn't really play a role in that person being able to walk and potentially perform their job as a lineman on the line of whatever team of the Super Bowl he was in, okay? So when we look at our bones, we are going to see that they are constantly carrying weight load, gravitational load. They are constantly exposed to the hormones and the nervous system output that is guiding our body through growth and through life. And as those hormones and those neural triggers and our weight bearing is occurring, we are constantly replacing and adding and transitioning our bones to better meet the needs of the body. So bones are going to constantly remodel themselves to best maintain our mineral reserve for calcium availability, phosphate availability, and then storage of calcium phosphates as we need to in our lifetime. All right, your skeleton, again, is going to constantly add to itself as we need to increase the strength of the bones because we need to meet the tensile lines that need to be maintained for weight bearing. If you ever remove that strength or that necessary weight bearing activity because you go to space, because you go to a less gravitational environment, or you become non-weight bearing, you get laid up in your bed for bed rest for a few days, or you have an injury where they immobilize your limb and you're not walking on it and weight bearing on it, you're going to see that the bone is going to respond to change and remodel itself so it can best put strong matrix-rich regions where the gravitational and the weight-bearing loads are applied. All right? And so the takeaways are that your bone remodels itself throughout your lifetime, and part of this remodeling process is to put the matrix where it's best utilized for weight-bearing activity. Now, there's this big event that happens in most of our female environment and lives called menopause, and it's a big change where we no longer see these radical increases in estrogen and progesterone hormones associated with getting ready to reproduce. And what we found is bone cell osteoblast populations are maintained by a nice estrogen surge every month. And throughout your lifetime, you have a population of osteoblasts building bone, and you have a population of osteoclasts taking away bone. And as long as the populations equal each other out, you don't see any extreme bone depositing or bone taking away. All right, and with life, we normally think of growing until about age 25. The osteoblasts and their activity is outnumbering what the osteoclasts are taking away. And so we grow taller, we add bone, we increase bone density. And then we find in our middle years that we are not really taking away bone and we're not really adding much bone because we're no longer growing. And the osteoblasts and the osteoclasts kind of find this homeostasis, this equilibrium where bone is not really being added or being taken away. But we see in women, all of a sudden, menopause happens around the late 40s, early 50s, and the population of osteoblasts significantly decrease. And so we know there's some type of estrogen-related osteoblast monitoring that occurs. And when the estrogens are gone, because we're no longer reproducing and building and adding estrogen to the uterus to grow and thicken up, and estrogens to tell the brain that we're viable in producing an offspring, we see that the osteoclast then population becomes more active than what our remaining osteoblast population is able to lay down for bone. And so what we'll start to see is a process of bone deterioration with age. And it's a natural phenomenon, and it's more pronounced in women because they have a more pronounced drop in their steroid hormones at menopause. Men are going to continue to see testosterone levels drop at a certain age, and that lower testosterone levels is going to, just like in women, see a decrease in osteoblast population. But it's less pronounced in men because their testosterone levels are not as significantly dropping that we see in women with lack of egg production. All right? So a natural process in the skeletal system is that we grow bones when we're young, and we add bone matrix, bone density. We find an equilibrium in our middle age, and then towards our later years, we see that bone loss is going to always be at a greater rate than bone laying down, bone growth, bone demand, and we are going to see eventually everybody shrink, everybody undergo decreasing bone mass and bone density, and eventually everybody is going to have an increased incidence, if you live long enough, for fractures to occur in some critical areas and critical locations of our bones that can then lead to, broken hips, broken spines, humps, twisting, leaning, and loss of height. Okay. Now, another big part of our bones is we constantly add to the matrix and take away from the matrix. And remember, most of the matrix is calcium. So what we're going to see is that there is a hormonal control of making sure that the calcium being deposited is not too much, so our blood calcium levels maintain a certain amount, and our calcium release from the matrix is not too fast, too much. So again, we maintain blood calcium levels. Right? And that is a big component of what the bone is doing. It's holding and storing calcium and phosphates for us, so on a rainy day when we need it, we can get it, and on a day when we have too much, we can store it for later on. All right? Now, other than age, other than estrogens, other than the calcium handling hormones, there are other ways we can push bones to grow, bones to hold matrix, hold density, or decrease it. And it comes back to load-bearing activity. So one of the big things you'll see as you grow is there's a push for do load-bearing exercise, do load-bearing activity. Walk as much as you can. And the reason why that comes into play is exercise and load-bearing activities is another trigger, another stimulus outside of estrogen, outside of testosterone, outside of your calcium handling hormones to drive bone cells to lay down bone matrix faster than the osteoclasts take it away. So exercise is one of the means at which, outside of growing, outside of estrogens, outside of testosterone and reproductive pushing, we can add bone matrix, add bone density, and try to increase our starting point for when it happens and age starts coming into play. We have as much as bone dense areas of our body as possible. Okay, and so what this is trying to show you is that if we do nothing, we are going to see that we won't ever potentially get as much bone mass, and then when we start to lose it, which is going to be a natural phenomenon with age, we have less bone to lose, and so we're going to end up with osteoporosis and osteogenesis and bone fractures and lower height and lower bone mass at an earlier age. But as a male or a female, if we can try to increase our bone mass in the earlier parts of our lifetime with nice weight-bearing exercise and weight-bearing stimuli, we can start with a higher bone density, so when we hit those critical time points of menopause and low testosterone happenings, we end up with more bone to lose, and we can maybe hold off on getting the osteogenesis, osteoporosis events, and loss of height. All right? The other way to do this is to, of course, avoid going to space. So the whole thing in the news for future going to Mars, for living on the ISS for a year, the International Space Station, is we put our bodies in a low density, low gravitational environment. And we see that bone loss occurs even in young estrogen-rich females and young testosterone-rich males. Bone loss is occurring at a faster rate than what it is on Earth. And so we know gravitational forces are one of the big drives to help us deposit bone in our matrix. All right? So one of the big things we have to overcome with going to Mars is if it takes us 6 months to get there, how can we keep our bone mass as high as possible in that low gravitational environment? So one way to do it would be to get us there faster, but right now that's not feasible with our fuels and with our rockets. So then if we're going to spend 6 months in low gravity and microgravity, can we exercise? Can we, some type of device, load bear, weight bear, press on our bones and load them and exercise with that load-bearing G-suit on in space to minimize the bone density loss. So there should be some really cool stuff that comes out as we, again, try to get ready to go to Mars or put astronauts in space for long periods of time. And I'm really interested to see how that Scott Kelly and his brother Data comes back, because he did grow 2 inches because he didn't have gravity pulling down on his bones, and he did lose muscle mass compared to his brother that stayed on Earth for the year. Okay. The other big way to push bones is to, of course, give it the nutritional building blocks to build bone. All right. So to be able to lay down bone matrix, so a growth pattern for endochondral ossification. In order to turn the bone matrix into a full bone matrix, you have to give the bone cells that are going into that area and the chondrocytes that are leaving that area the nutrients they need to transition from a matrix of cartilage to a matrix of bone. Same thing with the intramembranous ossification process. The cells that are going to take up residence in this now dermal tissue and convert it to bone tissue need to be given the nutrients to build the matrix from a dermal tissue matrix into a bone matrix. And what is it you need? Well, if I need to put calcium into the matrix, I need calcium in from my diet. If I need phosphate into the matrix, I need to bring phosphate in from my diet, because I can't make those molecules in my cells without bringing them from the outside environment. We are going to need to make vitamin C, so collagen can be synthesized by the cells. We're going to need to make vitamin A come in from our diet, so I push my osteoprogenitor cells to become osteoblasts and increase their activity. I'm going to need vitamin K and vitamin B12 to help push synthesize other bone proteins and to help make hormones that trigger calcium deposit and calcium handling from our bone cells. All right. So remember, in the skin, we wanted vitamin D3. We want calciferol. And calciferol, vitamin D3, eventually is one of the ways we help bring calcium in from our diet. So again, we need to have the building blocks, but we need to also have the cofactors and coenzymes that allow these cells that are going to then take calcium and phosphates and calcium and carbonate and collagen and put it into the matrix around them. All right. For hormones, again, we know estrogens in menopause and androgens in puberty are going to play a role in pushing bones to grow, to lay down matrix, and then maintain that matrix and maintain that bone density for a good portion of our life. And once those estrogens and those testosterones decrease with menopause, decrease with age, we know that the matrix of bone doesn't stay as dense and the bone osteoblast population decreases. So we know steroid hormones play a big part in bone regulation, but it's not the only one. Growth hormone and thyroid hormones are part of the growing process in young kids, and if you don't have growth hormone and thyroid hormones, you don't grow appropriately, you don't grow correctly. So we know that they're going to be a role playing in the bone growing ossification processes. Outside of those hormones, we know glucocorticoids, cortisol from the adrenal gland is going to play a minor little role in bone maintenance. And we know that the calcium handling is going to be by two main hormones, one from the parathyroid gland, the other from the thyroid gland. So calcitonin and parathyroid hormones, right? And so these hormones are not really worried about calcium levels in the bone. They're worried about calcium levels in the blood. And you need calcium in your blood because you need membranes to have calcium inside or outside to be able to be a second messenger, to be able to be a role player in for neurons, release of vesicles. We know that muscle cells need to regulate calcium levels because calcium plays a role in driving contraction. So calcium handling of the blood is very important. And the two hormones from our hormone endocrine system of calcitonin and parathyroid hormone are going to work in opposition of each other to make sure that if calcium in the blood gets too high, we can bring it down. If calcium in the blood gets too low, we can bring it back up. All right, and so the last big point of this chapter is how do we regulate calcium? All right, so go back to vitamin D from the blood, vitamin D from the skin, vitamin D from our gut population, from our diet is going to play a role in making calcitriol. And we know that calcitriol is going to play a role in the gut, in the kidneys, at helping us retain calcium and bring calcium in from our external environment. Right? So it is a player, along with calcitonin and PTH, parathyroid hormone, at making sure blood calcium is at a certain level. Okay? But it's not the only player. We know that parathyroid hormones embedded in the thyroid are going to work to make bone, kidneys, and the intestines increase their calcium in the blood. So parathyroid hormone is going to make the blood release, the bone release calcium, break down the bone so more calcium ends up in the blood matrix. It's going to make the kidneys do a better job of retaining calcium, so less calcium is in the urine and more calcium ends up in your blood. It's going to make your intestines work better at taking calcium in from your diet. All right? It is going to be opposed by calcitonin. Calcitonin's goal is when calcium levels get too high in the blood to push it out. So it's trying to push calcium into the bone, make the kidneys push calcium into the urine. Right? And so when we take these two hormones and vitamin D, leading to calciferol, that is the way we regulate blood calcium and then, in a sense, push more calcium into the bone or take calcium out of the bone. And when you look at it, again, those hormones don't really care that the bones are dense or not. They care about what is the blood calcium. So how do we keep bones strong? It's a combination of a few factors. It's a combination of exercise and mechanical stress and using gravity to help load the bones, keep tension lines on those bones, keep the osteoblast population putting matrix down. It's about having the nutrition that is bringing in the nutrients that lead us to being able to make collagen, lead us to being able to have calcium and phosphates, so therefore the blood wants to put it in the bone. And then it's about making sure that we maintain and handle calcium efficiently, making sure we keep the osteoblast population and osteoclast populations in balance. And so take all that together, and that is how we keep bones. That when we've gone through endochondral or endomembranous ossification, we keep them present so the bones are the right density, the right shape, the right way to maintain the skeletal support of underlying tissue and support movement. When bones fracture,
You can give them a variety of names depending upon how the fracture occurred and if it occurred in a specific bone. I expect you, and this is the end of Chapter 6, to just make some flashcards and get comfortable with identifying bone fractures. So look for a multiple choice question. Look for a question of what is a break in a bone along the shaft across the long axis. You should be able to identify that as a transverse fracture. All right, so get comfortable. I got to get to class, so I got to cut this short, but learn your different fractures and what they mean and where they occur and what kind of bones they are involved in. And that is the end of Chapter 6. And we have joints and a little bit more to cover, and then that'll be the end of our Block 2, Unit 2 material. All right, have a good day, guys.